Okay, so this time we'll talk about series solutions. Series solutions. So until now we were doing something like, let's say y double prime plus 3y prime plus 2y equal to 0. And we used to call this as what? Constant coefficient, linear, second order homogeneous differential equation. That was the full name of this equation, right? And the important word was the constant coefficient. And as I warned you, every time you take away some words from that constant coefficient, second order linear homogeneous differential equation, every time you take some portion of the descriptive thing from that differential equation thing, it gets harder, okay? So for a while we were struggling with the case when we were dealing with the case where it's not homogeneous. So if this thing on the right side is not 0, it was some strange function, then we had learned two ways to handle that. One was the method of undetermined coefficients, and the other was the variation of the boundaries method. Those were the two methods that we used. Now today what we are going to do is I'm going to remove the condition that these coefficients should be constants. So I want to make this something that varies. So for example, instead of 3, what if I had 3x? Okay. So all I did was I just put that x in there. Now suddenly this becomes 10 times harder than before. Just by placing that x there, this becomes 10 times harder than before. Because, for example, if you try to put this through Wolfram Alpha or these websites where you plug in the differential equation and they tell you what the answer is, you will get some strange functions. These functions that's not sine or cosine or exponential or any tangent, arctangent, none of that. I believe this will give you something like Airy functions. I think it has something to do with the Airy differential equation or something. And, you get some really strange functions that you've never seen before. Okay. So how can we handle those cases? Well, one way to deal with it will be to study the theory of Airy functions, and there are other functions that appear in this form. There's something called Bessel functions, hypergeometric functions. You have all these special functions that you can learn about, and then you can study their characteristics. But the problem is that those functions are much harder to understand. In fact, I believe some of the things they get out of hypergeometric functions are still not proven. So it's like basically uncharted territory there. Okay. So how do we handle the solution of this then? Okay. And the idea is to use something called a series solution. So instead of going for some known functions that will satisfy this, we will just say y is equal to some series a(n) x to the n from 0 to infinity. Now, why do we do such a thing? Well, because we know that all the basic functions that we can write down, they all have series representations, right? So for example, what is e to the x in terms of series representation? 1 plus 1 over 1 factorial x, 1 over 2 factorial x squared, plus 1 over 3 factorial x cubed, and plus da da da. It just works this way. So if you wrote it, it would be like 1 plus x plus 1/2 x squared plus 1 over 6x cubed and plus da da da. That's how it looks like. You learned this in when you were learning Taylor series. Maclaurin series of e dx is this. And you also know that sine of x is x minus 1/6 x cubed plus 1 over 120 x to the fifth minus da da da. And cosine x is 1 minus 1 over 2x squared plus 1 over 24 x to the fourth minus and so on. So those are sines and cosines. So because e to the x sine x cosine x has these power series representations, and anything you can think about, like x times sine x will be just multiplying by x to this thing, or sine 2x will be replacing x by 2x. So any of the functions that we wrote as solutions so far would have a representation in power series. Now the good thing about power series is that it's more expressive than just having e to the x sine x or cosine x. It can express a whole variety of functions, even those functions you have no idea that existed. Okay? Because it's simply, all you're saying is, to know what a function is, you just have to know these coefficients. Knowing the coefficients fully will tell you what that function is. Okay? Yeah. Now, in very, very specific cases, when you get the power series of that, you will find that the power series is a power series of a known function. Then you can come back and say the actual answer is one of these. But usually what you're going to get is none of these, and you will just have to leave it as that solution. And if you want to know further, you can go to some books on special functions, and they have power series representations of all these other functions that I talked about. You can search them up and see which function it corresponds to what you have. Actually, there is a system where you can convert all these numbers that you get to those special functions. Those are called hypergeometric functions, and that can be a way to write down the solutions. But for this class, all we will do is just say, I have an equation like this, and I'm looking for a solution of this form, and plug that into it here, and I just figure out what the values of a/n's are. That's all we want to do. Okay? Yeah. So since that's irrelevant, you don't need to know these. So let's just erase this one. I'll erase the big ones. Erase this. Okay, you might have forgotten what sigma notation is, so let me try to explain what sigma is. Sigma is for summation. It's the Greek letter sigma is the Greek letter s, so it's for sum. It always carries an index, and the index starts from some number and it ends at some number. Because this top one is infinity, it means that this index starts from 0 and it never ends. Okay, so what are you doing? This really means, first, when n is equal to 0, you plug in this 0 in here, and you get a0, x to the 0th power, plus comes from, the plus comes from this summation sigma. Okay? And then we've handled the case when n is 0. What's the next number after 0? It's 1. So you plug in 1 here and 1 there, and you get a1, x to the first power. And the next number is 2. So when you plug in 2 and 2, that's a2, x squared. And then a3, x cubed. And that's what it means. And you may complain, why write it in such a cryptic fashion when you can write it like that? And my answer would be that it's much quicker to write this one than writing that one. Okay? But what you should be able to do is, whenever I write this, in your head, in your mind, you should be able to translate this into this form, and only by being able to go back and forth quickly, you'll be able to understand what's going on. Okay? If you can't go back and forth between these two notations, it will be really hard to understand what's going on. Okay? So that's really crucial. Okay, so now I have to plug this into the equation, and in order to plug it as an equation, I have to solve it, right? Let's differentiate it. Now, what would you get if you differentiate this? Oh, this is, x to 0 is just 1, so this is really a0 by itself. So what do you get if you differentiate this? 0. Constants differentiate to 0. How about this one? What do you get if you differentiate this? A1. Yeah, that's x, so if you differentiate, it's 1.
Yeah, that's not.
Okay, x squared, if you differentiate x squared, you get
2x.
2a2x. Okay. And if you differentiate 3x cubed, you get 3a3x squared. Now let's try to rewrite this in terms of the sigma. What does that mean? It's this one you don't start, so it's like a, let's see, 2 and 1, 3 and 2. So it's always 1 less, right? And also you have 1, 2, 3. Well, you can do that, or you can just differentiate this. That may be quicker, right? If you differentiate this, what do you get? N comes down, an x to the n minus 1. And you can see that this is exactly the same as this description, right? For example, when n is 3, you got 3a3x squared, 3a3x squared. Same thing, right? So you don't have to write it this way to get to the next stage. You can just simply differentiate this. Okay. However, there's one thing that you do understand by doing this differentiation. It's that the one that corresponds to n equals to 0 will be gone if you differentiate, right? So instead of starting from n equals to 0, where should n start? 1, and it ends at infinity. It's still an infinite series. It starts at 1. Yes?
But wouldn't if you start at n is equal to 0, it would just be 0?
That's a good point. So Hannah is saying that even if you start with n equals to 0, you will get 0 times something, so it wouldn't hurt to start from 0. Okay. However, in terms of bookkeeping, we will have to do some bookkeeping after we plug that in. It will be helpful for us to start at 1 rather than 0. Later on, we will do something called Frobenius method. In that case, it will turn out that n equals to 0 doesn't produce 0, and in that case, you will still start from n equals to 0. So you will be able to, you will have to do it that way in the later, the harder cases. For now, we will start from 1 because the very first one is gone. Okay, now in the same way, if you differentiate again, what would you get? N minus 1 would come forward, right? So you get n times n minus 1, an, x to what power? N minus 2, right? And where should n start from?
2.
Okay. Now what we do is we just plug in everything into this equation. Right? So let's try to plug everything into the equation. So y double prime is sigma n equals to 2, infinity, n minus 1, an x to the n minus 2, plus x times sigma n times an x to the n minus 1, and then plus, actually there's 3x, I forgot to put the 3. It's not x, it's plus 3x, right? And plus 2 times sigma n equals to 0 to infinity of an x to the n equal to 0. So that's the differential. That's what you get once you plug in these ansatz, these power series into the left side. Now let's simplify this further. See, this is just endless sum of terms. You multiply 2 to it. What can you do? You can distribute the 2 to each individual term. So that corresponds to putting the 2 inside. Okay. So we have sigma n equals to 2, infinity, n times n minus 1, an x to the n minus 2, plus sigma n equals to 1 through infinity, 3 n, a, n, n, and then this x times x to the n minus 1, what's that? X times x to the n minus 1. It's just x to the n, right? Because this is x to the first power minus 1. And then plus sigma n equals to 0 to infinity a n x to the n
For the 2.
equal to 0. Yes?
For the 2 at the
Oh,
last
2.
one.
2. This is what we get. Okay, then after this we have to do something called shifting, and then we have to do a lot. Actually, this thing will probably take another 10 minutes, so I guess we should stop here.